speakers of our weekly colloquium. He is also an alumnus of the Archbishop Presidency College. After his BSc, he went to Calcutta University for his master's and PhD and became a faculty member there. In 2006, he became a full professor. And later on, from 2019 to 2023, he was the Vice Chancellor of Academic Affairs in Calcutta University, and also in 22-23 for several months, he was the interim Vice Chancellor. So, Professor Chattopadhyay is one of a few, group of people who essentially pioneered the field of astrostatistics in the Kolkata area as well as all over the country. As astrophysics students and researchers, you know that in the last 30 years, there have been accumulation of a lot of astronomical data, with many of which are publicly available. Many of you are using those data, and you understand that rigorous statistical analysis is required to get astrophysical information from those data, and the field of astrostatistics essentially employs statisticians, astronomers, as well as computer scientists to do that. And Professor Chattopadhyay has done a lot of research on those areas. He has published more than 100 papers, and several PhD students have worked under him, with him, to sort of develop novel methods and effective methods to apply statistical analysis to astrophysics data. And right now, he very recently superannuated from the Department of Statistics of Calcutta University, and is is a visiting professor at Indian Statistical Institute now. He has also been a fellow of the West Bengal, with the West Bengal Academy of Science and Technology, and also the International Statistical Institute, and various other very reputed institutions. He has been visiting. He has held visiting positions at several institutions in Canada, Australia, and France. So we are eager to hear from him about application of statistics in astronomy.
Thank you. I must thank Ritavan and Chetana for inviting me in this colloquium. So primarily, I must say that I am not an astrophysicist. So it may not be possible for me to explain some of the astrophysical concepts. I am basically a statistician. But I'm trying to do some work in this area. The particular work that I will present here, that was the last joint work with Tonuka. She was from astrophysics, my late wife. And her contribution, this is the last unpublished part of her. So I'm just presenting this one. Now, before that, so while actually my association with astrophysics started in Tayuka, Pune, particularly through Professor Ajit Kimball. And he first told me that we need, before me, there was no associate in Ayuka from statistics. I'm the first person, I think till now, I am the only person who is an associate of Ayuka from statistics. Because he told me that now, the present state, the astrophysicists, they need statisticians very much because of this big data situation and doing something with it. You know that this data science, that concept is so popular these days. I think astrophysics has a real application because in many cases, astronomically or physically, it may not be possible to explain some of the cases because something is unknown to us. But we have the data. So even through the data, it may be possible to find out the science, what is happening inside. So in that way, data science has a great meaning here in the astrophysics. So some of the basic, this astrostatistics part, this is started from Professor Yogesh Babu and Feigelson, they're in the Penn State. They have started a center here, astrostatistics, and the first book on astrostatistics is by them. Actually, when I was previously in ISI, I just got that book, and that created my interest in astrostatistics initially. And there are many such books. Gradually, this came into the market, and you may just see how the things are going. So now, when I started working in astrophysics, what I found that the problems usually when you try, there are some inherent statistical applications. It's primarily identification of homogeneous groups of objects. That was very much a common problem in astrophysics. And we find that there are several clustering methods which are very much useful there to find the proper groups in the group of data. That is one technique which is very much useful in machine learning technique. And the classification of objects, how to classify objects into a proper group and identify their, which group they belong. And another problem is multidimensional situation. You see that there are several such parameters, we call it variables. So several parameters and they are correlated parameters. So mostly when I am just looking at the papers, in astrophysical journals and others, usually physicists, they work with one or two variables at a time, and then they look at the various separately. But it was necessary in many situations to look at the total scenario because they are interrelated. So this multivariate scenario is very much important. And in some cases, the number of variables is so many, you need to reduce the dimension. So the dimension reduction techniques are also very much useful. And you know that the most popular technique is the principal component analysis. And but I say that for the first time in astrophysics, we use the independent component method because most of the data, they are non-Gaussian in nature. And for the non-Gaussian data, it is to reduce the dimension, it is necessary to use which is a signal to separation of signals from the noises. ICA is in many areas, and in astrophysics also we have used it. So it helps you to identify the proper dimension in that way. So that ICA is another technique which is very much useful. And the prediction problem is always there. And for the prediction, different types of regressions already they are used, like say lasso and some shrinkage methods, penalized regression techniques. These are also very much used. And obviously the Bayesian analysis is an important part, and the statistical inference. But these are mainly the techniques. But if you look at the data, the first problem you will feel that if we want to apply statistics in a particular, say for statistical inference, we assume that this is a sample. Okay? This is a random sample. Because without making this assumption, it is not possible to make inference using any statistical technique, which is the confirmatory. Exploratory part is there, but the confirmatory. But in astrophysics or astronomy, this concept of sample is very difficult to say whether it is a proper sample or not, because the universe is unknown. So I am considering, I am working with some stars or the galaxies. The data we have got it from the telescope and that within their limit. But there may be these days some new things are coming. You can see that some which are not at all possible to see. James Webb telescope and others, they can send the data. So that is a big problem there. So whether I can consider a particular part as a sample, but we make some assumptions. We're assuming that the universe is homogeneous and isotropic. I think this is the most crude assumption that one can make. But the astrophysicists always say that the distant universe is homogeneous and isotropic. I can't, I have no meaning to me, but they say why this.
That's the
cosmological concept. But this is accepted. Anyway, that is one problem. But if we look at on the data part, there are some ways to check whether it is a proper sample or not. That is called sample completeness check. That is very popular in astrophysics. What they do, for a particular variable, they just normalize it. Normalizing says that is reduce the dimension into 0 to 1 by making the proper transformation. That is called V by Vmax test. So this V by Vmax test, actually what is that? They reduce the range into, say, the range 0 to 1. And we know that if the sample is properly uniform, then the mean should be, what should be the mean? Sorry? 0.5. So if the distribution is properly uniform, the mean should be around 0.5. So they test for that. If the mean is around 0.5, they say that the sample is complete. And if not, they say the sample is not complete. That is a physical concept, but it has many limitations. Primarily, you're considering one variable at a time, and you're assuming transforming into the uniform distribution. There are many situations, in fact, theoretically, it can be proved that the marginal distributions are uniform, but the joint distribution is not at all uniform. So it doesn't mean that when the marginals are uniform, the joint distribution cannot be complete at all. There is a multivariate. So we have developed one trace to test the completeness of the multivariate sample in that. That is one statistical problem involved here. So there are many such statistical issues which are inherent in the research, and that's why this astrostatistics is an important part of the research in astrophysics. That is the motivation behind it. There are some works. Initially, I started working with many other authors, and it helped us to identify some of the multivariate effect on the different say objects. Particularly, we started with working with, say, the galaxies and the stars. One particular, that there's a very famous problem of gamma rays. That is, how many possible origins are there in the gamma rays? Gamma ray burst, and it is the first work where we identified three possible. Previously, two sources were identified. They divided it, and in this paper, we identified three possible origins of the gamma ray burst. So there are many such situations where we work with data and identify the.
So do you remember? So in that, you mean the short and the long?
Short and
but there is a medium.
Long burst.
The time scale.
T50, T90 on the basis. Even that identification of parameters, that is also a challenging problem. You have the gamma rays. So from the gamma rays, the astrophysicists, they identify those parameters, say T50, T90. Actually, these represents the characteristics of the gamma rays. So that is very interesting how they.
What is the parameter?
Relevance of the parameters? Whether the parameter is actually giving you the proper scenario. That is a very important thing to say. Okay, now this particular work is say study on star formation history of the nearby galaxies. We use some Bayesian approach. This is joint work. The astrophysical part is mainly due to Tanuka. Other three we are statisticians. So now. So what is the motivation? The motivation is this. I think you know much better than me. That is this star formation in galaxies. That is a very important issue. And this is not at all possible to directly estimate this rate because you have to count the actual number of stars in a galaxy, which is impossible. So there are many physical methods, indirect methods to estimate this star formation rate. I have used different notations to identify the scenario. That is, SFR true is totally unknown because we can't estimate that one. So there are some physical estimates, SFR tilde, that is on the basis of some physical phenomena that is used by different authors, say using some FUV plus IR, etc., etc. It's one parameter at a time. They have used one parameter at a time to identify, compute this star formation rate. So the proper estimate, that is SFR estimate, is in demand under the because this SFR is affected by many parameters, not only a single parameter. So if I physically try to find this star formation rate on a single parameter, it may not be true. It may give you some wrong answer. So it is necessary to consider many parameters together to find this star formation rate. So the problem is this unknown. So there are several physical models of this SFR tilde which suffer from different limitations, particularly being on a single parameter. So I've selected one of these proposed model because you see, if we, that is a statistical problem. If we want to apply some regression, then what is actually regression? Regression is the opposite of progression. So in order to actually regression is not prediction. That is a misconception. Is actually regression means it is opposite of progression. So we have to build up a model on the basis of whatever is available, and we use this model for the future for prediction. So regression means you have to go towards the past.
Yeah.
Okay? And then you predict for the future. Now, this thing that is, to develop the regression models, I need data, but I have no data on SFR. If I want to predict SFR, I need some SFR, otherwise I can't predict. So the maximum, say the controversy against this work is this: you don't have any proper SFR value. But we have chosen one of the physical model-based values by Lee 2010. I don't know the reason, but astrophysicists say that this may be treated as the best measure of SFR. So we have taken that particular value as the true SFR, and the basis of that we have tried to identify, compute the.
So Lee and all, that is a
Theoretical, physical thing. They computed, estimated SFR. So finally, we have proposed a multivariate database estimate of SFR estimate and compared its performance with the above physical SFR tilde obtained by different methods. That is the gist of the book. So for the prediction part, we have used some Bayesian method. That is called Bayesian. Lasso is a very common technique that is a penalized regression. In case of it is called the L1 penalty we apply on the regression method to penalize to reduce the. Actually, I may explain the technique, but it will take another class to explain what is the lasso method. But lasso, you can accept that lasso is a penalized regression method, which is used to in some situation when there is multicollinearity in the data. Multicollinearity means when you use a set of independent variables, there may be the number is large. There may be inherent correlations among these parameters. And if it is strongly present, then your prediction will be wrong. So to eliminate some of them, because if two variables are correlation is 1, then we need not use both of them. I can just drop one. So that is our concept. So this helps you to eliminate some of the not necessary parameters, and so that you will get a good prediction model that helps. So is something like this. And so that is the technique for prediction.
And the penalty is if you add more parameters, then you get
the constant on the values of the.
No, when you say penalize, what do you mean?
Penalized regression.
What is the penalty? Penalty is this: some of the beta coefficients, that is the regression coefficients, we try to make them close to 0. We impose some constraint on the beta values so that some of the betas is reduced, which are not so important in that. So that I can eliminate those corresponding parameters. Penalty on the beta values. Now the parameters which we have considered for this to study this star formation rate, these are the parameters: axial ratio, absolute magnitude, log of the mass, radius, tidal index, surface brightness, and I think you know that these are some of the parameters which affect the star formation rate. So we have considered this on the basis of the data set that was developed by Carl himself in 2013. This development of the data set, that is also a statistical problem. Why? Because the different telescopes are working all over the world and the sources are not the same. So if we have different sources and if we combine them, we have to make proper adjustment of the data. That is called cross-checking. So proper cross-checking is necessary in order to build up a proper actual useful data set. That is one part. So this is the essay which is developed by Karachenship. Now, so to find, but another point is we have seen it is also physically found that this star formation rate varies over the different groups of the objects. So in the physically, they have provided rates uniformly, that is same for all the types of objects. But statistically, it can be proved that this star formation rate varies over the groups. So initially, we have identified some of the possible groups, and then we predicted the star formation rate for these groups separately, not the same prediction equation. That is another achievement of this work. Okay. So we haven't used K-means. You know that K-means clustering is a very popular method for clustering, but K-means suffers from different types of limitations. Primarily, it is only useful in the situations when the clusters are, say, spherical or circular, because we use this Euclidean distance there. And many other problems. And it is very much dependent on the initial choice of K. So how to find K, that is a big problem. So we haven't used that K-means clustering. We use this mixture model based clustering technique. This is, the idea is very simple. What do we assume here that this actually, this is a combined CD for PDF. This is a mixture of all such PDFs. These corresponds to the different groups. That is, we assume that there are G such groups, and we have a mixture of the objects from the G such groups in a single. It's very easy. And these are the weights. This tau is, these are the weights, and the sum is. So, and for these individual group densities, Fk, we assume that these are multivariate. So that is the PDF of the distribution. And so the set of a finite mixture model, this is called Gaussian mixture model based clustering. Gaussian, because we have assumed that multivariate was normality. So Gaussian mixture model based clustering. So here the purpose, the target is to estimate this mixture parameters tau k and the mean and the variance of the normal distribution. And so these are the parameters to be estimated. Okay. And so what is the, so for this we have used, this is a very famous algorithm used in, I think physicists, it came from physics initially. This is the expectation maximization algorithm. What is this algorithm? We have a scenario, we have several parameters. So initially we choose some initial values of the parameters. We put the values there. We compute the likelihood and we maximize that one. We get a new choice. Again, we put the values. Alternatively, do the until and unless this algorithm converges. That is called the expectation minimization. Expectation maximization algorithm. So EM algorithm. So we have applied this EM algorithm to find out the estimates of tau, mu, and sigma. So these tests should obtain some initial values of the parameter mixing proportions. This one. Put the values. Given the initial values, that itself calculate the conditional probability that the ith observations comes from the kth group. So this is the probability. This follows from this direct application of Bayes rule. It can be proved from the Bayes rule, how it comes. Then the end step is now use the estimate of the mixing proportions obtained from each step, calculate new parameter values, say the eta k, and that is the sum of the mixing proportions for the kth group, and this give the effective number of data points assigned to the group k. That is the end step. So these are the steps that are involved to estimate the parameters. It's for EM algorithm. And then we get the new estimates by putting the previous estimates step by step. So continue these steps B and C until and unless this convergence. And for convergence, actually, we compute the maximum likelihood functions. And when the difference is not much, then we stop. That is called a EM algorithm. In short, this is the method. Statistically, there is some explanations are there. So now the question is how to find the number of groups, that is the G. So this we have done by using some Bayesian model that is called, there is a factor which is called base factor, and but the idea is the selection by this base factor and the posterior model probabilities. The idea goes like this: the several, suppose I don't know the number of groups. So M1 is a model, M2 is a model, M3 is a model with varying number of groups, and I have to finally select how many groups are there. That is M1, M2, Mk, these are the models. These are considered with prior probabilities P, Mk. Now, by applying the Bayes theorem, the posterior probability of Mk getting selected for this data, this is given by Bayes. I think Bayes theorem is standard. And from there, we compute this factor Bij, and if Bij is greater than 1, we choose Mi over Mj. That is, there are several models M1, M2, M3. You choose that model for which this posterior probability is higher. So
and then this PMT you assume uniform, or how do you determine the prior probability that because there is a prior involved?
this probability is
Uniform for all models.
So this is the final part of the, that is how to find out the number of groups. So by applying this technique, we have identified the number of clusters in the data.
So when you say that BIC will add a penalty to the log likelihood based on number of parameters, you mean that if you increase the number of parameters, then it will be penalized because it's easier to fit something with larger number of parameters.
So the steps we have followed up to this is this. So select a maximum number of components to consider our mixture model. Suppose it is Gmax. Suppose I assume there are 20 such groups. That is the maximum value of Gmax. Then estimate the parameters via EM and MAP estimation method for the parameters. Compute the BIC and then select the model which gives you the optimum answer. So I got the number of groups this way. And you see, this is the, from this you can find out what is the number of, optimum number of groups if I plot this number of mixture components and the Bayes criteria. And these are the inherent, these are the density and the box plots of the groups. Actually, we got 6 groups, but after that we reduced it into 5 because we have checked that 2 groups are performing almost in the same manner. So we have taken them together and finally you have considered with 5 groups.
So it's maximum at something like 6.
6,
Yeah, 6 seems to be the best.
6 max. So 6 is the group, and then you will convert it into the 5 groups because 2 groups are almost same. You see, there is another point here. I'm tempted to mention that you know that in astro there are many outliers. So how to take care of this outlier? This is a statistical problem. If there is a single variable, it is very easy to identify the outlier. It will be too far. For 2 variables also, you can take the scatter and identify them. But what happens if the 3 or more parameters together? How to identify the outliers? In fact, this clustering is one of the techniques where you can identify the outlier. If one of the groups contains 1 or 2 observations, then that may be considered as an outlying group in a multivariate setup. That is one way. Or you may compute the say the Euclidean distances of the points, and whose distance is far
Sigma.
then that may be treated. So under the multivariate setup, the detection of outlier is also a problem.
Important problem.
Important.
Complex problem.
Complex. So
but the groups are non-overlapping completely.
yeah,
So,
that technique is like that. So BIC criteria for selecting the optimal number of clusters was 6 clusters. So after performing a Bayesian lasso, we observed that the groups 4 and 5 had the same set of variables selected. So after merging these two clusters, we have the same set of selected variables for lasso. So also this GMMBC with 6 clusters and with 5 clusters only had a difference of only 94%. So we have concentrated on the 5 clusters rather than 4. And we have denoted these 5 clusters by G1, G2, G3, G4, G5. Okay. So now another point that physicists, they are very much in favor of looking at the data through graphs. I think this is the nature of the physics. So for this, we tried to show the physically how the groups are performing. So we reduce the dimension, and not PC or IC. This is another method. By this, we have reduced the dimension to plot the clusters so that you can physically look at the nature of the clusters. So we have used one method that is papered. This is this. Use this one. So by this you can see that how the groups are performing. In that 2-dimensional situation, we have extracted 2 of the directions, direction 1 and direction 2, and plotted the values. You can see the existence of the groups physically. Because when we have submitted our papers in many situations, the referee just requested for some graphical presentations. It helps them to feel the data graphically. So this is one way to look at the data graphically.
And these are the parameters which are
dominating
for
all the
groups.
There are altogether 6 such parameters, so we have reduced to the two important detections. And this is the lasso that you're asking me. This is the pin. Okay. And lambda is the parameter involved here. So but there is no penalty. We minimize the first part, and here we have imposed this. And this is the if there may be a squared one. There are several penalized methods. The sum of squares. This is sum of the absolute values. This cost max. So that is the lasso method. We minimize that one. And Bayesian lasso is some. There are some assumption on the prior distribution also there inherent. That is by Tischerand, is a very famous statistician, introduced this method. Bayesian lasso, and we have applied this. By applying this technique for the 5 groups, these are the prediction equations. So how to estimate the estimated star formation rate, log of that, for the 5 different.
So these 5 different groups are effectively 5 different models. Am I right?
The
Okay, the
objects.
importance of the parameters, those hydrogen bars.
Observation.
Classified the objects in 5 different groups, and for each individual group, you are
Okay, so
finding the star formation
in the
rate.
data set.
In the
It's
set.
like 5 different groups, and this is the star formation for each of those groups.
Actually, all the objects usually they don't perform similar manner. Star formation rate is obviously it is not the similar for all the. It varies with the gas components. Many things are there. So this will help you to identify the star formation rate for the groups separately.
And all this, so we can see that B by A, MK, M21, MD, so 6 parameters.
Right.
So all those were the initially you wrote a list of
Right.
parameters. Those are 6 or more.
6.
6. So all of those are contributing.
But
Some of those are-
this is a
Weightage is very
negligible.
less, yeah.
Even if all of them are not
Not
present in
all
all
of them
the.
are present in
That's
all.
right. Not
Theta 1 is not present in all.
That is the Bayesian lasso effect of this lasso. If we use a simple regression, then all must be there in all. Okay. I think it is not visible, but these are the properties, that is a table where these properties are listed for the different groups. You can see the number of objects here. This is the 104 objects in this. Here we have 56, here 115, something like this. The number of objects in the different groups and the corresponding membership of the groups and the estimates of the different. So these are means and the standard deviations are listed here. Now, actually, this is the contribution of the astrophysicist totally. So how to physically, this is the most important part of the work. After, in fact, in any clustering, this clustering has no meaning if you can physically explain this clustering. You can cluster any data, but this clustering will be successful only when you can say differently explain the clusters, the groups. They're performing in a different way. So here you can see these are the physical explanations. This is
Each of these groups, what
Each of
would be the?
what type specialties are there
Yes.
in the groups. Okay, say the G4 and D5, they're strongly rotating, if dominated, late time, largest size. They follow the Tully-Fisher relation, independent of environment like this. So these are the, after getting the data, you just look at the data and try to interpret this way. That will help you to explain the inherent scenario, what is happening, what are the differences physically. Okay. And you can see the fit there for the different clusters. It is comparison with a particular method. There are different physical methods. This is comparison with on the basis of MFUV. You can what is happening.
Oh, so this is the comparison between what you have estimated and
At
what is determined
by
from that
MFU.
tilde one is there.
These are for five.
Five groups.
Five groups. These are for five groups. Okay.
So the offsets are similar for each group. Means from MFUV, whatever you are getting and whatever you are getting from the
Predicted equation.
predicted equation, there are some
Differences.
differences. Some statistical fluctuations are there.
Okay.
For all the groups, it's the similar statistical.
No, not
fluctuations.
necessarily. Not if you see this reflects. It's not exactly same for groups. It varies. Particularly in cluster 4, it is
Four has more scattered.
more scattered.
Others are similar.
Mostly
Most comparable. Maybe one has a little bit.
Scatter is more in more. This
The
is
R is the correlation or something? Sorry.
no, that is the goodness of it. R square. Goodness of it. So this is another method. And this is some simulation actually, as we don't have actual values. So we try to simulate the values artificially to establish whether the work is good or bad. By introducing some error into that, artificially introducing, it is a very common technique. Some error into the model and then fitting it in different. So we have introduced errors in different proportions and tried to check it. And more or less it gives a good result.
These are random methods.
Random errors, normal Gaussian assumption,
Gaussian.
in standard normal, N0.
Correct.
These are the error you put it in
Model. We add some artificially, we add some errors, and then we predict it. Try to see what is happening. So these are the fits. So this is actually the conclusion, that is this SFR tree is difficult to measure. So many physical models in a particular wavelength, we have the values. The present model considers many parameters instead of the only one parameter at a time. The present model estimates SFRs only after clustering, not global signature. Present model compares SFR with previously estimated physical models. The present model also compares the Bayesian estimates SFR with the other models through statistical simulation. And most of all the cases is proposed values of performing more better.
Okay, questions? Or anyone?
So this is something where we have a lot of data and we are classifying them into 5 groups. And then we see that in some of the groups, some of the parameters are redundant, so we can not talk about it. But how different is it from if I consider those parameters and let's say we get a good fit and those parameters are very close to 0. So that would also make us classify them.
That will introduce noise into the. That is the problem of multicollinearity. You can check yourself. Suppose you have a big data and there is multicollinearity. If you fit using that particular data and use something different, perform different.
So that's like if you have a bunch of points you are fitting, it's mostly straight line, but you are fitting it with ax square plus bx plus c. So you are saying that you will get a equal to 0.
Yeah, but then I manually just use the next.
Right.
So that will be an algorithm itself.
Ah,
Okay. Other questions? Yes.
Reduce the series of loss we have shown to a straight line.
Yeah.
But there is some large from around the straight line, there is error.
Oh, so if you go to that good where you had the R square value in the plots. Yeah, so he's asking about the shaded region.
yeah. These are some error bars.
They are part of the parameters coming from the times. So I had a question from this actually. So you did all this and now you are finding that R square is 0.14 in one case. That means that the goodness of it is not very good.
Not very.
So that means that group 4, whatever you got with all this, it
is not
still not a very good
still
model.
not.
Or at least that whatever we got from the group is not commensurate with that, how this SFR is being
Yeah.
estimated from, let's say, the MHR,
MHR.
from the H alpha data.
Actually, these cluster 1 and cluster 3, they are performing, this method performing better compared with the
Yes. And the overall sort of astrophysics conclusion from this is that for say you showed that slide with the important astrophysical information. So for highly rotating galaxies, one kind of model should be used. For faint galaxies, another kind of model should be used. That is our conclusion.
Right.
If we
So the clustering itself, you are picking up those galaxies.
right. But
Even though you have not put the information that they are rotating galaxies.
Yes.
right.
Just from the data, you are saying that these are the parameters that are contributing this much for this group, maybe less for the other group. And then you infer what could be the physical reason why this parameter is not important.
when we have clustered, we have considered only the observation, that is the objects.
Right.
But here it is the converse one. After getting the objects in a group, we are looking at them.
And also not all parameters are suitable for all galaxies.
Correct.
Okay.
But is there using the random number generator? Can anyone reduce these forms?
So simulation.
Yeah.
Yeah, it is possible. You have to make proper assumptions.
The AI models are probably doing similar things, right? Where you have a bunch of parameters and you're trying to figure out which parameters could be set up.
Actually, you can artificially create the parameters.
Right.
What I try to build up a model.
Okay. Hidaka?
Sir, do you have other means of getting the prior knowledge to calculate by putting in the Bayesian formula apart from the observational data and the prior knowledge we are putting?
I think you're asking about the prior distribution.
Prior distribution.
Choice of prior is everywhere it is a problem in Bayesian technique, how to choose the prior properly. There is some trial error techniques. You can change the prior and see how it is. In case of conjugate priors, it is fixed. That is, it will perform best. But if you use some non-informative prior or say some other, then there it varies.
Like do we use non-informative priors?
Yeah.
So can I just add to that? So I think if I understand your question, one good example is a prior can also come from theoretical considerations. For example, suppose you are fitting you are trying to extract cosmological parameters. You know that the universe has to be flat. So that means omega lambda plus omega m must be less than equal, should be equal to 1. So this kind of priors also can be incorporated in because suppose there is a parameter and you are probing a parameter space that, for example, something cannot be greater than the speed of light, that you can put as a prior. So priors also, other than what sir is saying, you can have physical motivations behind prior.
Actually, the problem is of improper prior, the total integration may not be 1.
So from that we know that
Something is missing.
Something is missing.
Okay. Any other question? Yes.
So, all these